let's see if we can prove our guess for what the appropriate derivative rule is for a composition. So let's see if we can find the derivative of f composed with g. Remember, this is just f of g of x. Now, to put this sort of in context of our guess, what we really should do is name g of x. So let's give it a new variable name. Let's call it u. So what we're going to be trying to calculate is the derivative of f with respect to x, right? So the derivative of f as x changes. And what our guess was that this is the derivative of f with respect to u, right? The derivative with respect to this intermediate variable, times the derivative of u with respect to x. Okay? So the idea here is we have f. It depends sort of indirectly on this intermediate variable u, which really is g, right? The function u is sort of given by the function g, and u in turn depends on the ultimate variable x. Okay, and what our guess is telling us is that the derivative of f with respect to x is the product of the derivative of each step along the way, right? So the derivative of f with respect to u times the derivative of u with respect to x. Okay, so we're expecting these two derivatives to show up. So there's going to be some kind of derivative of f, and then also there's going to be some kind of derivative of u, but remember, u is really g. So this is really, we're expecting dg dx to show up somehow, right? And it's nice to have some idea of what you expect to show up, because remember, part of what makes this limit definition of the derivative hard to use is that often we have to create the pieces that we need out of nothing, and it's hard to know what pieces to create if you don't sort of have an idea of where you're headed. So let's see. By definition, this derivative is f of g of x plus h minus f of g of x over h. Okay. Now, so really the only piece of this that has anything we could really work with is this sum. We're kind of stuck because we don't know anything about the functions f and g. It's possible that there's no nice sort of sum formula for these functions f and g, right? Like there was with the trig functions, right? If we had a sine of x plus h, maybe we could use the sum formula for sine, but we don't know anything about g. It might not be sine, it might be something else. So we're kind of stuck with this x plus h here. There's not much we can do with that. But on the other hand, we're expecting dg dx to show up. And dg dx, that's the limit as h goes to 0 of g of x plus h minus g of x over x plus h. Well, we have over h. We have an h in our denominator, but there aren't any g's, right? All of the g's that we have here are packaged up inside of f. If we're going to make this derivative, dg dx, show up, there should be some g's not packaged up inside of f. In other words, what I'm saying is, it seems like in this numerator, we ought to have g of x plus h minus g of x. But we can't just multiply by this, because that would change it. Right, we have to keep things balanced. We can multiply the numerator by g of x plus h minus g of x if we also multiply the denominator by the same thing. Right, that won't change the ultimate value of this whole thing. It's hard to know if this is a good thing to do, right? It looks a little suspicious. Definitely it's allowed, it's okay, but it's hard to know if it's really going to help. But it's the only idea we have, so let's go for it. All right. So now that we've decided to do that, we need to decide how to rearrange things in a useful way. But remember, we're expecting this derivative to show up, this g of x plus h minus g of x over h, right? We have the numerator we wanted. Let's get this denominator with it. to do that, why don't we take this denominator, g of x plus h minus g of x, and move it over here. So we're going to swap these denominators, which, according to the rules of fractions, is okay. So this gives us f of g of x plus h minus f of g of x over g of x plus h minus g of x. And then over here we have g of x plus h minus g of x over h. Now things are starting to look up a little bit, because if we use the product rule for limits, this is the limit as h goes to 0 of f of g of x plus h minus f of g of x, missed a parenthesis up here, over g of x plus h minus g of x times the limit of, as h goes to 0, the limit of g of x plus h minus g of x over h. And actually, it's only okay to do this if these individual limits exist, this limit and this limit. And this second limit definitely does exist. This is just the derivative of g, right? So really, to be fully justified in using this product rule for limits, we need to know that this second limit exists. And actually, there's a sad fact. It might not. There are some special weird cases where this second limit doesn't actually exist. Now, I'm going to kind of sweep those details under the rug, because it turns out that in almost all cases that we care about, this limit does exist. But it turns out that if g sort of, you see, since we're taking a limit as h goes to 0, it's possible that g near x, it's possible that g oscillates so wildly that this term, g of x plus h, is actually equal to g of x infinitely many times near h equals 0. And if that happens, then this limit doesn't exist. But that almost never happens. For all of the derivatives that we're going to be calculating in practice, that doesn't happen. And so this argument that we're using works. In the other situations, it turns out that there is a way to fix this whole proof so that you get the same derivative rule in the end, but let's not sweat those details. Okay, so as long as g of x isn't too crazy near x, then using the limit, the product rule for limits here is okay. Now this second limit, that one's just g prime of x. Now we need to figure out what this limit is. Well, you can see that there's a function we have sort of this function inside that's changing a little bit, but then in the denominator we have the difference of these same things. So remember at the beginning we named g of x. We called it u. And so g of x plus h minus g of x, that's really a change in u, right? So this denominator here is really a change in u. Now f of g of x plus h minus f of g of x, so this first piece I'm going to leave alone for a second. F of g of x, that's g of x, that's u. Okay, so what goes in this parentheses? Well, it should be g of x plus h, but if we rearrange this here, it says that g of x plus h is g of x plus delta u. So this is, and g of x is just u, so this is really u plus delta u. And we're taking a limit as h goes to 0, but as h goes to 0, g of x plus h has to go to g of x because g has to be continuous because it's differentiable. So that's another way of saying that delta u has to go to 0. Well, look, for this second piece of the derivative, we've essentially reproduced the derivative of f. So this is the derivative of f, but what we're putting inside isn't x, it's actually u. So the derivative of f at u times the derivative of g at x. But remember what u is. U is g of x. So we get f prime of g of x times g prime of x. And there's our derivative rule. So this is the derivative of f composed with g. And this does indeed verify our guess, right? Because on the left here, if we write it in Leibniz notation, on the left-hand side we have the derivative of f with respect to x. Remember, we have f depending on u, which depends on x, and u is really g of x. So f, the derivative, the rate of change of f with respect to x. In Leibniz notation, the way that we wrote this, or the guess that we had, was the derivative of f with respect to u, that's this, the rate of change of these two, times the rate of change of these two, the derivative of u with respect to x. But remember, u is really g. So this is df dg dg dx. So you can see that in Leibniz notation, this derivative rule that we got is the guess that we originally had. The one extra wrinkle that this Newton-style notation makes clear is that the derivative of f with respect to g, this is actually evaluated at g of x. And the derivative of g with respect to x, that's just evaluated at x. So our guess for the derivative rule for composition in Leibniz notation is correct, but we have to be careful about what values we plug into these individual derivatives. Right? In the derivative of the outside, we plug in the old inside, and in the derivative of the inside function g, that gets just x. All right, so this derivative rule, let me just write it out. Derivative of f composed with g, and remember this is, another way of writing this is f of g of x. So the derivative of this whole thing is the derivative of f with g of x inside of it times the derivative of g with just x inside of it. So this derivative rule, it's the derivative rule for composition, but what it usually gets called is the chain rule. Because composing functions is chaining them together, so this is the derivative rule for when you chain things together. And this formula can be hard to remember, but the way that I think about it is just whenever you have an outside function and an inside function, it's just the derivative of the outside function with the inside function in it times the derivative of the inside function. So this is kind of how I remember it. Another way to remember this is just as sort of a chant to yourself that to take the derivative of anything, you differentiate the outside and multiply by the derivative of the inside. So the short version of the chain rule is just always multiply by the derivative of the inside.